month, so
Oh yeah.
I've I've been a hermit. Um, Literally left the house yesterday. This is my friend's birthday, and I'm just looking around,
Uh-huh.
and I see people, and I'm
Yep.
like, I forgot like people exist.
hmm
Like it's like random strangers, and I'm looking around. I'm like, I'm just wow.
Yeah, yeah.
That's the point where it's gone to.
hmm
But yeah, so I took the Altius test. Not
Yep.
gonna lie, I think like it was like I don't know, the most similar to AMC that I have taken.
Oh, interesting. Yep.
So
hmm
I think it was like the way they test you is like I feel like better than Blueprint. I mean, it's all subjective, but
hmm
not gonna lie, it was like I've been learning a lot. I've been reviewing it this time very, very, very intensely. So yeah. Um, so I sent you a passage I wanted to go over for it.
That's a couple.
Yeah, yeah. Yeah. So there's a chemistry and physics passage that I wanted to go over.
Yeah.
The issue is Altius, they have a retry limit of how often you can like see the retry the exam. So I don't know if you want to like we would have to go over the passage through the like pictures if that makes sense. So like we don't see the answers, you know what I mean?
Yeah, sure.
Should I share still?
Yeah.
Okay. Okay. All right. I can start reading it.
hmm
So D-Limonene is a terpene found in the peels of citrus fruit that holds promise as an anti-cancer agent. Um, I think a buzzword could be terpene. That's like a precursor to cholesterol. Um, Anti-cancer maybe.
What else can you tell me about terpenes?
Terpenes, they are the building blocks of steroids. So it goes like terpene, then I think isoprene or the opposite, and then steroids and cholesterol.
So, um, what about isoprene?
Um, what about it? Like a terpene. I forget what the order is, the first two, but I know they create steroids, and then that leads to one of them being cholesterol.
Yeah.
Cholesterol.
So,
Yeah.
so terpenes will have an isoprene as its like fundamental unit or backbone. So, what do you remember anything else about an isoprene?
Um, so there's like monoterpene, triterpene, like it two isoprenes make a terpene.
So, so isoprene is the backbone, and it's a five carbon molecule that looks like oh, that looks like
It's like
the,
double bond.
Mhm. Basically that. That's isoprene, five carbon, um, like unit for, and then terpenes will be using that as a building block. Um, so you can imagine like I guess yeah, okay, whatever.
All right. Um, in the presence of oxygen, D-limonene undergoes autooxidation by a free radical chain reaction, forming hydroperoxides.
Yeah, what does that look like?
Um, it oxidizes itself
Hmm.
in the presence of oxygen. Yeah. Oxidizes itself, free radical reaction.
Yeah, like so an example could be, diatomic bromine that can break apart like this. And these are single barbed arrows,
Yep.
meaning that it'll turn into two bromines with a single electron, aka
Mm-hmm.
radical, right?
Mm-hmm.
So this is like, for this type of reaction, you want to know like, the initiation step, which is this, the continuation step, which would make more of these, and then like a termination step when they can combine to form the diatomic bromine again. So that's essentially what's happening here. So that's what they mean by the hydroperoxides. Okay.
An experiment was designed to study the rate of oxygen absorption by D-Limonene with changing hydroperoxide concentration. The amount of gas produced, yeah, the amount of gas produced was measured with the gas beret, and the hydroperoxide content was determined by iodometric titration with sodium disulfate.
Okay. So the iodine, like the bromine, can also have that type of auto like reaction to make the free radicals. So those free radicals can combine with the free radicals of the hydroperoxide to like, turn it back into something that isn't a free radical.
Mhm.
Okay.
Okay. Wait, I'm slightly not understanding this. Hold on.
Hmm.
So there's the autooxidation reaction
Hmm.
with the free radical, okay, form hydroperoxide. Um, so what they're measuring the amount of gas, like why?
Oh, so they are trying to study the rate at which oxygen is absorbed by the D-limonene with changing hydroperoxide concentration. So they measured the gas produced um using the gas burette, and then they measured the amount of hydroperoxide by doing an iodometric titration with sodium thiosulfate. So yeah, so they're I guess using those two ways to measure like the rate of oxygen absorption and changing hydroperoxide concentration, I guess.
Okay, and it's yeah. The wait, hold on. I don't know where I left off, but
This was,
uh,
yeah.
in this procedure, hydroperoxide is reacted with ion and starch for 15 minutes before titrating with thiosulfate, complex iodine, and starch, and is blue in solution.
Mhm.
The structure of D-limonene, limonene, and the titration reaction is shown below.
Mhm. All right, we see D-limonene here, and we can see like I guess the double bonds and stuff that you would expect to see in some type of terpene. And then they have reaction one, ROOH plus 2H plus 2I minus yields I2. plus ROH, alcohol, plus H2O. So what is this ROOH?
Peroxide. Hydroperoxide.
Uh-huh. Good. And we can see that that yeah, it can react with the iodide ion um in this step here. And then in reaction two, the iodine could be mixed with the thiosulfate to produce, I guess, more of the iodide ion. And it seems like the thiosulfate seems to maybe have complexed with itself or something. It seems like something happens there with, you have two and then turning into one. So, okay, that's reaction two. And what's below this, if anything?
There's one sec.
Mm-hmm.
Um,
Um, so ROOH, okay, yeah, represents the hydroperoxide products from the auto-oxidation of D-Limonene. The reaction data were used to generate figure two. Figure two, oxygen absorption and hydroperoxide concentration. So we have x-axis time in hours. Oh, we have two y-axes. Okay. Y-axis on the left is what? Um, ooh, okay. What MEQROOH? MEQ? Is that what is that?
I don't know.
Polar or something? Well, okay. It's something that's
Yeah.
supposed to represent the amount of hydroperoxide. Okay. And the y-axis on the right, oxygen absorbed, and then the black squares, O2 absorption. Uh, and then the gray squares, the I guess the amount of the hydroperoxide. Um, they seem to be somewhat proportional. I mean, until you get to like 8 hours, and then the amount of oxygen absorption decreases, and the ROH doesn't. Maybe I guess it starts to become a little flatter.
Mm-hmm.
But okay. And then further tests of oxygen absorption rate were performed in the presence of acid and base. The results are shown in figure two. Oh, wait. Isn't that figure two?
Mm-hmm.
So might be a mistake. There
No,
should
no, no. So they're talking about first hydroperoxide concentration, I think,
be. Mhm.
and then they're gonna tell us about oxygen absorption rate. You know what I mean?
This had both of them, and then in the presence of acid and base would be another figure.
Oh, okay.
Is there another figure?
Mm-hmm.
Oh yeah, there it is. So they just made a typo.
Oh, typo for figure two, probably.
Yeah. Because
Okay.
it's figure three, right? So
Yeah.
okay, so figure three, O2 absorption in the presence of acid and base. So okay, we see that it seems like less of it in the presence of acid, right?
Yeah.
Compared to uh
So,
uh hold on. This is an acid, this is an acid, this is an acid, and this is sodium carbonate, which could be considered a base. That seems like exactly the same as the citric acid. So I guess because citric acid is weak. So, and then water is like the highest amount of oxygen absorbed. So I guess the more acidic something is, the less oxygen is absorbed, perhaps.
how'd you know citric acid was weak?
Uh, because I'm pretty sure it's no, that's not acetic acid. I figured it was weak because we generally know strong acids.
Mm.
Sulfuric is an example.
Hmm.
Phosphoric is like a triprotic acid, and anything that's like triprotic or diprotic, like, are not going to be strong because when it loses its first proton, it'll turn into like the conjugate base, which then can also be an acid to you. It can also be the acid because it can then lose the second proton. So and also like the sodium carbonate, I can, that's the base, and I see that in the graph, it's pretty much the same as the citric acid one. So why would an acid give you same results as a base? Uh, it must not be a very strong acid, right?
Strong acids are sulfuric, nitric.
Typically, the ones with, so if we're talking about oxyacids, ones with a higher oxygen amount. So sulfuric acid, for instance, compared to sulfurous acid, right? The one on the left is sulfuric. It has a larger amount of oxygen, so it's a stronger acid. Then same thing with like HNO3, HNO2. Nitrous acid on the right, nitric acid on the left. The one with the higher amount of oxygens is stronger. And then there's, of course, this. So the one with four oxygens is the strongest. It's perchloric acid. But think of it as hyper, meaning more. Because, well, I should maybe start off like this. The one with three oxygens is chloric acid.
Yeah, yeah, yeah. And then
This
yes.
is chloris. And if
Hmm.
you want to go even stronger than chloric, it could be hyperchloric, which is shortened as perchloric.
Hmm.
If you want to go less than chloris, it'll be hypo, meaning less. So for the oxyacids, um, whichever one has a higher amount of oxygens is stronger. Um, but yeah, phosphoric acid, though, sure, it can have a high amount of oxygens, like four oxygens, but it's polyprotic. Polyprotic acids are not going to be particularly strong, I guess. I mean, even though sulfuric acid is a diprotic acid, um, yeah. I guess in general, yeah, you will know the strong acids. Um, and they're pretty much the ones that I wrote out here. Yeah.
All right. I think that's everything for passage, honestly. So
All right.
pretty short passage, but the questions
Mm-hmm.
I got killed on. So
Yep.
I think I got, let me see how many I got because this like killed my score for CP.
Uh,
If I got the whole passage right, I would have gone like a point higher on the
uh-huh. So they said
section.
blue in the passage or something. Let me
Yes, yes.
uh
It's here. It was pretty last sentence.
comp the starch thing. I was a little worried about the starch thing because I didn't really see it in any of the reactions here, but okay, but if okay, so if hydroperoxide is reacted with iodide ion and starch before titrating with the thiosulfate, so before reaction two, I guess, complexed iodine and starch is blue in solution. So let's see, I'm gonna write it down. So iodine connected to starch is blue, and before
Wait,
thiosulfate. Yeah.
my reasoning for this, it was probably like
Okay.
bad.
Wait. Um, so the so wait. Blue is before the thiosulfate, right? Right? They said hydroperoxide is reacted with iodide, ion, and starch for 15 minutes before titrating with thiosulfate, right?
Mhm.
And, when it's, complex iodine and starch is blue, right? That means that if we then add the thiosulfate, it should no longer be blue, right?
Mhm.
So I think it should be blue to clear.
Mhm.
So
Yeah, I mean, my reasoning, I
yeah.
just thought because it said blue that like once it would react, it would be clear, you know?
Uh,
That's all
sorry.
I thought.
Tell me that.
I just thought that because it was said it was blue, and I thought that iodide ion was like the complex iodine.
Uh-huh.
So I thought that it was I thought it was blue already, and then it would become I mean, sorry, it was clear, and like I thought the complex iodine was what was the result of the reaction with starch, and then titrating with thiosulfate.
Yeah. So we have your hydroperoxide plus iodide ion yields. Oh, I guess there's also starch yields iodine, you know, connect being bound to starch, and that turns it blue before the thiosulfate. So that should be blue. And when you add the thiosulfate, it should no longer be blue.
Why? Is that a titration understand like mechanism thing?
Oh no, it seems like so when they say complex iodine and starch, I think what they mean is what I take that to mean is iodine being bound to starch. So if you add the thiosulfate, like we do in reaction two over here, we reform the iodide ion, right? From what? So like here, okay, so yeah, actually we have this here already. So this is the hydroperoxide, this is the iodide, and they didn't write starch, but just imagine starch being there. And then you get this. So the I2 we can consider to be similar to iodine being complexed with starch, and that's going to cause the color to be blue. But then when you do reaction two, where you add the thios sulfate, this I2, which we can consider to be iodine bound to starch, turns back into the iodide ion. So it's almost like this. Right.
Okay.
So,
I complex iodine,
uh-huh.
that's when it's connected to the starch.
Yeah,
Where is the starch here? It's not in any equation, right?
it's not, yeah.
Okay.
So, so, but what we're doing in reaction one is when we react the iodide ion with the hydroperoxide, we get we no longer have an iodide ion, right? It's iodine.
I too. Mm-hmm.
Now, complexed iodine, like it ends in, INE, so this should no longer be a an ion, right?
Mm.
So
Okay.
yeah, but if they're telling, I mean, they're telling me that it should appear blue before the thiosulfate. So going off that in the choices, I would choose something that isn't blue after the thiosulfate. So mhm.
Okay.
Yeah, let's look at those choices again.
Oh, well, here, I'll just, this is the problem.
All right, so can't be green to blue, right? We never talk about anything being green, right?
Mm-hmm.
That's out. Blue to green should be out because again, we don't talk about anything being green, right?
Mm-hmm.
Then it's clear to blue or blue to clear. Now, they told us in the passage that the that this thing is before the thiosulfate and that it's blue, right? So if we're adding the thiosulfate, we should no longer have it be blue.
Yeah.
So that could be another way of doing
It's a
that.
miscomprehension question then.
Hmm.
Miscomprehension mistake, sorry.
Um,
Um, okay.
yeah.
All right, next is this. Uh, so I don't know. So I actually got one out of four of them correct. I don't know which one, but this is the way I approach this question. Like this is one of the last passages I did. So keep in mind I'm under time crunch, but I saw this. And so suppose researchers need a purified sample of D-limonene with minimal contamination. To accomplish this, D-limonene could be doubly distilled. So I did not spend much time on this, I remember. I literally just put A. I put under nitrogen atmosphere because nitrogen is an inert gas, and so it wouldn't contaminate anything.
So what would contaminate?
Um, Probably air. Like if it's not a vacuum,
So I mean, air has nitrogen in it.
true, but it has also other things, doesn't it?
Yeah, what in particular?
Oxygen, free radicals.
Well, oxygen, yeah. The oxygen we know from what they told us, right? Uh, didn't they say in the presence of oxygen, limonene auto-oxidizes and stuff?
Hmm. Okay.
So when they say contamination, they mean like oxygen.
Okay.
So okay. Now I think D is like if you have the wrong idea of contamination, like
Hmm.
if you think contamination's like, something like bad, it would make
Yeah.
like use a filter or purified air.
Yeah.
But we know that it's the oxygen that we don't want. So we don't, it doesn't matter if it's filtered or purified. If it's air, it has oxygen. We don't want that. UV light, that typically, I mean, I don't know if they said anything about it, but in the example that kind of I started with, like this happens, or how about this? So you know why hydrogen peroxide, like if you buy it, it's in like an opaque like bottle.
No, but no, I mean now because you're giving me the context clue, like sunlight and or
Yeah,
UV, whatever.
yeah. So like oftentimes these reactions happen due to like, some type of high energy light. So and that's why and like so yeah, hydrogen peroxide, HOOH, H2OH, in the presence of light, uh turns into water, essentially. So that's why they're in the opaque bottles that light cannot travel through. So UV light should cause that type of free radical, like kind of autolysis kind of thing to happen also. Um, and then below atmospheric pressure, let's see.
Yeah, that's a little trickier.
Yeah, I mean,
But
if you have it at below atmospheric pressure, like that can affect perhaps like the boiling point. And since you're talking about distillation, but that shouldn't change. I mean, that'll change the boiling point and stuff, but that shouldn't change like whether it's contaminated or not. Whether it's contaminated or not entirely depends on oxygen. So, and yeah, it wouldn't make sense to change the pressure either because we're not trying to change like, the rate of distillation or anything like that. So yeah, if you use a nitrogen atmosphere, as you said, it's an inert gas and it doesn't change the pressure. So so we get to do exactly what we want to do without oxygen entering in.
uh,
Yeah. In like national archives and stuff where they have like the Declaration of Independence and the Constitution and stuff, they're kept inside of a hermetically sealed kind of, box that's filled with nitrogen. Uh,
mhm.
because the oxygen would cause degradation of that document. So to preserve it, it's kept in like a nitrogen atmosphere. Because that's a way for you to keep the same pressure, uh, but removing the oxygen, which is a highly reactive, thing.
Mhm.
So, yep.
Okay.
So you have the right idea here with thinking, it's an inert gas.
Mhm.
Therefore, it won't but yeah, but I guess the fundamental thing with that question is understanding that by contaminant or contamination, they need oxygen.
Okay. Um, Next was this. So the auto-oxidation of D-limonene in the presence of O2 results in a mixture of products. Which structure is least likely to be detected as an oxidation product of D-limonene?
Okay.
So yeah, here, well, first of all, in terms of how it looks, this sort of looks like, right? So um,
Okay.
yeah, so oxidation is you're adding an oxygen group.
Um, which one of these is the most different?
Mm, on the test, I thought D. Now, I'd say C.
Okay. Why? How is it different?
Because I mean, C, it's C, like there's a carbon and carbon, and then it's a carboxylic acid. But like in all the others, it's like the carbon's O, it's oxygen.
One oxygen, one oxygen, one oxygen, two oxygens,
Okay.
right? So for the oxidation of the limonene, so remember the biochem generalized redox stuff pathway?
Probably.
So something with so if you have like a double bond and you oxidize that, what would that turn?
Yeah. Epoxide.
Uh,
Wait, like
mhm.
oxide double bond.
Yeah, do you remember the thing where it's like, all right, let's say we have just an alkane like this, and if we oxidize it, so oxidation in Gen Chem, it's loss of electrons, oxidation,
Yeah,
but it's more useful here to think of oxidation as either loss of hydrogens,
yeah.
gain of oxygens, or gain of bonds to oxygen. So
Okay,
what
so it can, you can get like an OH and H, you can get an OH and A and OH from the double bond. Like,
so the alkane though, when this gets oxidized, it loses hydrogens to turn into
oh yeah.
an alkene, right?
Yeah, yeah.
And now when the alkene gets oxidized, what would it turn into?
Like a triple bond.
So let's see
Yeah.
what else can happen.
Well, something else. There's multiple things. You can have like an OH and an H group from the double bond.
Uh-huh. So we let's think about it like this. So we've already got rid of a hydrogen, so now let's try adding an oxygen
Yes, so
to get
we
an
can get an
alcohol,
OH. Yes, yeah.
to get an alcohol. And then
Mm-hmm.
when we oxidize the alcohol, we can
Ketone.
think of that as adding bonds to oxygen. So you can
Yeah.
get either a ketone if it's a secondary alcohol that you're oxidizing. If it's a tertiary alcohol, you can't oxidize it. If it's a secondary alcohol, it can oxidize into a ketone and it cannot be oxidized any further. If it's a primary alcohol, it can be oxidized into an aldehyde, which can then be oxidized into a carboxylic acid, which can then, so now we've added okay, from here to here, we're adding an oxygen. From here to here, we're adding a bond to oxygen. From here to here, we're adding another oxygen. And then that, meaning that's the other oxygen right there. So then after that, we can just add another bond to oxygen to get CO2, right?
Hmm.
So this generalized redox pathway is super, super useful. So it would be good to have this down. So now if you look at limonene over here, what do we see? Well, we see a double bond here, right? And if that gets oxidized, it would turn into what?
An alcohol group.
Yep. So like that, right?
Hmm.
That can work. Um, Now what if we oxidized it again?
Ketone A.
Uh-huh. So that can work. And hold on. If you oxidize it again, you'd get C, but this epoxy.
No, C is adding a carbon.
Oh,
Unless I'm mistaken, C is adding a carbon.
no, you're right. You're right. Hmm. Yeah. Okay. Okay. That's super confusing. Okay. Yeah. I guess I would have thought D as well. What? Because just going off of this, but so okay. That means that from this, it would. Oh, you know what?
Mm.
JK. So what? So this is a ketone. Ketones can't be oxidized further.
Hmm.
So this is impossible. So yeah, good catch because you are adding a carbon there. But but if this wasn't,
Oh, I get it.
yeah,
That's what they want us to realize,
yeah,
right?
because because the ketone cannot be oxidized further. If it was an aldehyde, it could be oxidized further into the carboxylic
Yeah.
acid. So yeah, I probably when I took this, like I probably chose D too because so it's weird. It's like at first I was like, okay, C is the most different because it has two oxygens. No, that's not the reason why, it's wrong. The reason it's wrong is because the if you oxidize limonene once, you get B. Oxidize it a second, again, you get A. Oxidize it a third time, it would seem like it would be carboxylic acid, but this is a ketone. It can't be oxidized further. So it's impossible for C to be the case. Now, how can it be like an epoxide? I think that's so typically for that we have, or the example I think of is, it's a bad drawing of it, but like, uh, like RNA, like this can attack that. I think that could be the thing.
Yeah, yeah.
Yeah.
Wait. Um, if it so wouldn't it like only it would attack it, but OH would have to be like pronated, right? So it could leave or something?
Um, yeah, I think that the uh so 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 okay, so from this, it can form that alcohol like that, but it can also form the epoxide, um, I believe. Um,
I don't think
yeah.
like epoxy reaction like is this like in the scope of the MCAT though or no? Because like
Uh,
I'm just saying like knowing all the different.
well, yeah, yeah. So, okay, you know what? I think so it's something like it's going to be the reaction with, let's say, something like this, and it was some type of with a double bond. It was something like this. The
Yes.
epoxide can be formed, yeah, with that. Yeah, this one is tricky. So I think that this is a so in this situation, you're between something you do not know if it's right or not, but you know C is impossible. So if you know C is impossible, but you don't know anything about D, that means D could be possible. So in terms of like what to choose, you would choose what you know to be uh impossible.
Yeah. Okay.
Yeah. But yeah, that was tricky. I probably got that. Imagine we got like the same things wrong.
That's crazy. Yeah. I mean, when I saw that, I was like confused when you sent that.
Yeah.
Uh,
When it comes, yeah,
okay.
for the average for the 523 plus scorers for this test is a 507.
Yeah. I mean, I don't know. It's like it's kind of scary. I don't know because I'm like
Hmm.
on biochem, there was a decent amount of questions that like
Hmm.
I I got right on the second attempt.
Yeah,
So
that's good.
I know it's good, but it's like
Yeah.
still the timing is like getting me up. Like CP was a little more. I didn't get as much right the second time still.
Hmm.
But biochem it was like at least half. I got right the second time.
Yeah, that's good.
So I think what I'm gonna try next is just if I can't answer a question in less than 10 seconds, like flag and go move on, see how much time I have at the very end to review.
Yeah, yeah. Like, I mean, the 10-second thing, I mean, I say like a minute and a half should be like the longest. Maybe if you want, you can shave that down to a minute. Because, yeah, the ideal thing is that, you get to review the flag questions after you've seen everything.
Yeah.
Yeah, I think so like that, I would say like a minute and a half. If you want, you can shave it down to a minute. 10 seconds, like you're not going to get anything in 10 seconds. So,
Okay. Yeah, I mean maybe that was like a underestimate, but or overestimate, whatever. But yeah. All right. This is the last one here. So this, by the way, I guessed on. Or like kind of yeah, basically guessed on. The
oh,
D designation in D-Limonene is an abbreviation for Dextrorotary.
mhm.
Dextrorotary. This indicates that D-Limonene rotates polarized light. So has to do with
Dextro,
uh-huh.
dextro means right-handed. S is, oh wait, actually, yeah. Levo is the left-handed one, which would correspond to sinistrol S. So let's see. Well, so dextrorotary means that it's gonna rotate clockwise, rotate plane polarized light clockwise. Levorotary will rotate plane polarized light counterclockwise, so we can get rid of counterclockwise. And I could see this over here. Um, hmm. This is okay. I can so typically okay. So yeah, typically dextrorotary will be having an R configuration, but I'm looking at must and could, and I'm thinking, so like if you have a racemic mixture of something, um, like what is that?
It has the RNS 50/50.
So
It has a mixture of products of R and S
yeah, an equal
product.
amount of the two, right?
Yeah.
And that is that gonna be optically active?
Um, yes.
So if we
Or
have
actually they cancel each other out.
uh-huh,
So no.
now that's if you have 50% of each enantiomer, right?
Okay.
Now let's say that it wasn't like that. Let's say it's like 51% R and 49% S. That would still that would be optically active, right?
Yeah.
So let's say the R1 rotates clockwise like 14 degrees, and the S rotates counterclockwise. Oh, let's say this is plus 14, minus 14 degrees. And if you have equal amounts of the two, they'll cancel out, right?
Yeah.
Now let's say we have 60% this, 40% this.
Well, it's gonna rotate like right.
Uh, rotate.
Rotate. It's gonna be dextrorotary, like
Yeah.
more dex 14. Yeah.
Yep.
Plus 14.
Yeah. So that would make it B. But D would be a very, very good choice. And that I would have probably chose, or I probably did when I took it, but I notice now the difference between must and could. And yeah, you can still have something that's dextrorotary, um, with having R and S.
Yeah, I put D.
Yeah. So I mean, yeah,
Um,
so you were able to at least eliminate A and C, and that's what makes this tricky. You have the right idea, but yeah, I think the must and the could be uh the clue here using kind of this type of example.
mhm. Okay.
Mhm.
So next is this.
Oh, and I would say the dextrorotary, even though I wrote R for it, the real definition is that it rotates plane polarized light clockwise. Okay. And the levorotary rotates plane polarized light counterclockwise. So it's not that if it's dextro, it has to be R. If it's dextro, it just means it rotates clockwise.
Oh wait. Um.
Hmm.
Well, honestly, I'm right there here. Um. I'm sorry.
Hmm.
So wait, you're saying
Yeah. Yeah. So dextrorotary. Well, I'd write dextrorotary just because the thing is the D.
I'm just my spelling is like scuffed this word. I don't even
No, you're right.
Dex
You're good here.
Dex Tro Ro Ta Tori. Oh my
Yeah.
God.
What?
All
Yeah,
right.
it's okay. But basically, this just means that it rotates plane polarized light clockwise. It doesn't necessarily mean R. Yeah. Yep. And then
Okay.
levo would be the other way around. Yeah.
All right.
Mhm.
So
Yeah.
next
Mhm.
is this, and I just want to make sure. I was like really upset when I got this wrong because I mean it's like a freebie question. So the reaction below is characterized by which chemical processes? So um yeah, it just shows a reaction. It's just asking for oxygen reduction.
Let's
And
Gold is 0 here. It's what here?
right, so on the right, it would be 3 plus 3. And so +3 means that it is losing electrons, which is oxidation. So it's oxidized. I also saw 1 and 2 nitrate. It's like opposite. So like the choices can't have 1 and 2, right? So then I look at nitrate, and nitrate is what got me because I was like, I don't know what I missed, but I was also a little confused because I thought so like I thought when they said nitrate. I thought it meant like, right, so you have the
Oh,
nitrate on the left.
is it a thing with nitrogen versus nitrate or something?
Yes, yes,
Okay.
yes,
Um,
exactly. And I don't know if maybe it was a mistake on their part, but I don't know.
all right, let's see. So we have NO3 minus, and this is -2 times 3 -6, and this should be +5 for the nitrogen. Here, this is -2. This should be +2 for the nitrogen. So the nitrogen.
Gains electrons.
Oh, I see. Got it. The nitrogen gains electrons, but the nitrate gets reduced.
But isn't reducing gaining electrons?
That's a good point. Okay, you know what? The nitrate, it's yeah, they mean, I believe, the nitrogen in the nitrate.
Okay, but if it was nitrate, would it
Yeah.
not be getting it would be getting oxidized
It was nitrate.
because
That
it goes from -1 to 0, no? The whole charge.
Yeah, that's weird. I think that there's we when we do redox like this, it's like Gen Chem redox, and it's just for individual like elements or atoms. So they messed up here. They really just mean nitrogen.
Okay.
Yeah.
Yeah, I mean if it was
I see-
nitrogen, yeah.
Yeah, I see what you mean. So if they really mean nitrogen, um,
Okay.
yeah, gaining electrons. So, yeah, that right.
Got it. Yes. 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 Okay. And all right. Last question. This, yeah, it's got wrong. Didn't understand it. The magnetic field in an MRI machine is created by a current in the solenoidal wire. The magnetic field in a solenoid is given by the equation below, where N is the number of turns per unit length, I is current, and mu is a constant. If the strength of the field at the center of the solenoid is known. What additional information is needed to determine the current carried in the wire? So it gave us magnetic field, so B equals mu Ni. Now, my thinking here, they asked what additional information is known for the current, what needs to be known. And so they already gave us a number of turns per unit length. So I automatically remove the A.
Wait, so here, capital B is the um strength of the magnetic field, right?
Yeah.
So they're saying that that's known, right?
Okay.
And this is a constant, so that's also known, right?
Mhm.
And they're asking us to find current, which is I. So the only
Oh
thing,
my God.
yeah,
That's crazy.
yep. So nothing about that or that or that is here. So yeah, should just be N, right?
Damn, okay. Yeah, I was overthinking it. Ah,
Tell me what
okay.
you're thinking.
I was thinking they asked for current.
Hmm.
So I was thinking V equals IR. And
Yeah,
so voltage is there, so I chose voltage.
got it. Uh,
Wow, okay.
well, we would also need resistance,
Yeah, resistance, yeah.
right? But from the equation that they give us, they tell us, what we have, so we can just use that. Yeah.
Metal of which wire constructed can be used to find resistance,
Resistivity.
right? Resistivity, sorry,
Yep.
resistivity. Um, and then radius of the solenoid, when would that ever be used? Is that like the ILB equation or what?
Hmm. Yeah.
Or
Like, yeah, I guess like when you have like the coils and stuff going into it. Yeah.
an MRI, it's magnetic, like it's circular and magnetic. Like it creates a magnetic field.
Hmm. Yeah, basically, uh, you can make a magnetic field by so we know that a moving charge creates a magnetic field, right?
Yeah.
So if you have a wire that's, like in a circle, it's going to create a magnetic field that's going to be like inside of that circle. So if you have like a bunch of coils, it'll go in through that, creating that uh thing. A solenoid. If you look up solenoid, like
Hmm.
Google or whatever, Google image, you'll
Yeah.
kind of see what I mean.
Okay.
But you're basically creating coils of a wire. Um, and when you have the coils of a wire, it'll create a magnetic field that'll be within the loops of the coil.
Mhm. All right. Um, sounds good. Also, do you mind if I pay you like at the end of the week, or you prefer things to come in? You don't mind there.
Yeah, if you want to do that, that's fine. You do that.
Okay.
Hmm.
Yeah. Got it. All right. Well, I'm gonna see you tomorrow.
Yep.
Then at 4, if I'm not
Yep.
mistaken.
Yep. Yep.
And I should be looking to take AMC calling through Saturday. That's still in the plans.
Yeah.
Okay. And then I guess from there we'll assess if like I'm still gonna be taking January 11th.
Okay.
So yeah.
All right then.
Yep.
So yeah, I will see you tomorrow. Okay.
Okay. Bye.
Take care.